Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asghar, and today we are going to extend our previous lecture. The named was the thermal analysis of inorganic materials under the subject of applications of TGA and DSC. So far, we have discussed some about the TGA and the different events, thermal events that can be diagnosis by the thermogravimetric analysis in inorganic materials. So we have already studied some of the applications of DTA and DSC, including the quantitative chemical analysis of alkaline earth metals and calcium and magnesium analysis also in the dolomite ore, and we also talk about the kaolinite in clays, and today we are going to discuss another example of clays, which is the hectorite. Hectorite having the formulas Na0.3 Mgli3 Si4O10 FOH twice is actually a clay mineral with a similar structure to that bentonite, which is a quite famous ore. It belongs to a smectaceous groups. It has a soft greasy texture and feel like modeling clay when squeezed between the fingers. So it is one of the more expensive clay. This expensiveness is actually due to its unique thixotrophic properties. The main use of hectorites are in cosmetics, for making lotions, soaps, creams and shampoos, and coating and inks. It is also employed as a molding sand in metal casting and as a filler in paper industry. We have already discussed that kaolinite is also used as a filler in paper industry, and and almost 50% of the kaolinite was used in paper industry. So hectorite is also have the same property of filler in paper industry. It has a great capacity to absorb and to adsorb because of its high specific surface. It plays an important role in industrial water purification and discoloration of oil and some other liquids. Hectorite geologically samples are usually associated with large amount of calcite, in some cases with varying amount of dolomite. So dolomite is also included as a kind of second ore with the hectorite. Thus, most published thermal analysis curves reflect the thermal analysis behavior not only of the hectorite but also for the carbonates. This figure is actually shows a typical DTA curve of this hectorite. At an endothermic peak at delta T of 119 degrees Celsius is caused by the interlayer water loss, whereas the 742 and 838 degrees Celsius peaks are actually due to the dehydroxylation, or we can say the carbonate decomposition reactions. A narrow exothermic peak at about 1110 degrees Celsius is followed by endothermic peak at 1135 and 1255 degrees Celsius. The latter are probably due to the formation of clinoenstatite. So this is all about the DSC or DTA curves of hectorite, which gives the quite comprehensive information of decomposition of hectorite clay. So the next is the concrete and mortars. Concrete is actually the mixture of cement, clinker, water, gypsum. Gypsum is calcium sulfate with two water molecule, and aggregates such as quartz, limestone, dolomite, and slag. Clinker is produced by the reaction of calcium oxide, silica SiO2, alumina Al2O3, and ferric oxide Fe2O3 at about 1500 degrees Celsius to give tricalcium silicate. We can also pronounce tricalcium silicate with C3S, dicalcium silicate C2S, tricalcium aluminate C3A, and ferrite solid solution of composition between dicalcium silicate and C6A2F, often represented as C4AF. The hydration and hardening of Portland cement takes place as a result of the following reactions, in which tricalcium silicate C3S is actually reacted with the water molecule and produce the C3S2 with 3 water of crystallization and calcium hydroxide, while dicalcium silicate C2S is combined with 4 water molecule and changed into tricalcium silicate with 3 water molecule and calcium hydroxide subsequently. The tricalcium silicate trihydrated derived from these reactions has extremely small particles and it forms a colloidal suspension. Calcium hydroxide is a crystalline solid which is obtained in both reactions. It is actually a crystalline solid, and the hydration products of other cement components are not generally described as producing Portland. If thermogravimetric analysis is actually carried out in carbon dioxide at atmospheric pressure, the first event will be the dehydroxylation at 400 degrees Celsius of any Portland present in the recently made concrete. So that would be the reaction like this. The calcium hydroxide, which is found in the crystalline solid, is actually changed into the calcium hydroxide and water, calcium oxide and water. But the amount of calcium hydroxide is very small amount. Old concrete, because of the reaction of Portland cement with carbon dioxide over many years. So that would be like this. Calcium hydroxide may react with the carbon dioxide gas and change into carbonate, calcium carbonate, and water. So it is actually shows the importance of this last reaction in thermal analysis of dolomite used in the recycled porcelain cement and an aggregate. So on the other hand, the DTA curves of ancient concrete, this is actually for the DTA curves of the ancient concrete, shows the existence of endothermic peak at about 570 degrees Celsius, as we can seen in this picture. At about 570 degrees Celsius there is a small endothermic peak. It is actually the existence at about 570 degrees Celsius. This peak is actually related to the allotropic transformation of quartz. So this is actually the indication of quartz transformation. Another component of concrete and mortars is gypsum. Natural gypsum formula is, we know that the calcium sulfate CSO4 and 2 water molecule. If 2 molecules of water are removed, the anhydrous calcium sulfate CaSO4 is produced. There are two anhydride forms, one which hydrates with water and the other which shows no tendency to react with water. This is actually insoluble anhydride. This figure shows the differential thermal analysis of calcium sulfate 2H2O sample heated at 20 degrees Celsius per minute. Crystallization water was partially removed starting from 123 degrees Celsius to produce the hemihydrate form. Hemihydrate form is actually the calcium sulfate CaSO4 with 0.5 H2O. It is also called the basanite or plaster of Paris. The second peak at 202 degrees Celsius, here we can see that, is actually due to the loss of hemihydrate 0.5 H2O to form soluble anhydride, which is the calcium sulfate. The exothermic peak between 353 and 375 degrees Celsius is actually the representation, the phase change to insoluble anhydride. So let's talk about the pigments. So in pigments, the first one is the Egyptian blue. Egyptian blue have the formula calcium CaCu and Si4O10. It is actually a very stable pigment which can be found in many works of art from Egyptian and Roman civilizations also. This compound can be synthesized in a thermobalance, heating a mixture of quartz, silica, which is actually silica, and cupric oxide, calcite, and a fluxing agent. This may be the sodium carbonate, borax, or lead oxide. Without these fluxing agents, the reaction proceeds very slowly, leading to an impure product which does not have the intense blue color of the pigment. So these fluxing materials are quite helpful for the impurity of the this Egyptian blue color and this pigment. With borax, for example, the reaction mixture forms calcium copper Si4O10 at about 900 degrees Celsius at a heating rate of 4 degrees Celsius per minute and remains stable in an oxidizing atmosphere to about 1080 degrees Celsius. Above this temperature, it decomposes to give off tridymite and a mixture of copper oxide and cuprous oxide due to the reduction of Cu2 plus to Cu plus as shown in this figure. However, the initial compound does not form again on cooling even through Cu plus deoxidized to Cu2 plus. The thermal stability of the isostructural compound, which is strontium SrCu Si4O10 and barium cuprate BaCu Si4O10, is greater than in calcium compound since they decompose at 1150 degrees Celsius, 1150 and 1170 respectively. Single crystals of calcium, strontium and barium compounds can be grown by using borax or lead oxide or sodium carbonate flux with the heating cycle of 30 hours at about 900 degrees Celsius, which we have discussed already. These crystals are similar to some Egyptian blue samples obtained from archaeological excavations. So this is the actually the TGDT curves showing the formation of Egyptian blue from calcite copper oxide quartz mixture. The next one is the extractive metallurgy. In extractive metallurgy, the first is actually the thermal behavior of AlF3H2O, aluminium trifluoride with 1 water of crystallization. Aluminium fluoride is used as a flux in the electrolytic reduction of alumina Al2O3 to produce metal aluminium. In wet process, the anhydrous fluoride is prepared by heating actually trihydrated aluminium fluoride. This is trihydrated aluminium fluoride. This thermal decomposition involves 3 stages. For example, in this figure shows that TG and DT curves for aluminium fluoride trihydrated and the system AlF3 3H2O magnesium oxide at a heating rate of 110 degrees Celsius per minute. The first stage with the temperature in the range from 100 to 277 degrees Celsius and a mass loss of 33% is actually related to the loss of 2.5 molecules of water from AlF3 3H2O. So this is actually the loss of 2.5 water molecules from this compound. The value of mass loss in the second stage, which is about 6.9%, correspond from the formation of anhydrous aluminium fluoride. This is actually the loss of another 0.5 water molecule from the AlF3. As temperature exceeds to 380 degrees Celsius, aluminium fluoride reacts with water to give alumina, which is Al2O3. So this is all about the TGDT curves of AlF3 3. So this is actually the TGDT curves of AlF3 3H2O and the system AlF3 3H2O magnesium oxide at the heating rate of 110 degrees Celsius per minute. And this is the whole process, that is the whole thermal behavior of AlF3 with what 3H2O. So in first step is actually AlF3 with 3 water of crystallization is heated, and then we will get the removal of 2.5 water molecule from this AlF3 3H2O, and that the product that we get is AlF3 with 0.5 H2O. In the second step, after continuous heating, then the rest of the 0.5 water molecule is also removed and we will get anhydrous AlF3. So the anhydrous AlF3 may have combined with the water molecule and change into alumina and HF, Al2O3 and HF. This is the total description of thermal behavior of AlF3 with 3 water of molecule, and this is actually the TGDT curves of this compound. The next is the thermal oxidation of covellite. So thermal oxidation of covellite is actually covellite usually exists in small quantities associated with other sulfides such as chalcocite, which is Cu2S, and chalcopyrite, which is CuFeS2, and bornite, which is Cu5FeS5. So it is exist in small quantity with these kind of sulfides. Heating covellite in a oxidant atmosphere causes actually the formation of copper deficient compounds at low temperatures, and the oxidation of sulfates and oxides at high temperatures. So if we heat the covellite in quite low temperatures, then we will get the copper deficient compounds, while at high temperatures we will get oxidation to sulfates and oxides. Some of the scientists carried out the TG-DTA test with covellite samples at 20 degree Celsius per minute in dry air. So this would actually the TG-DTA curves of covellite. Some of the scientists analyzed that the evolved gases by use of coupled FTIR equipment. The first stage is actually the decomposition of small amount of covellite to give digenite. Digenite is actually Cu1.8 sulfur, and the oxidation of covellite to produce copper 1 sulfide. These reaction is actually give an exothermic peak in DTA curves and a mass loss in TGA thermogravimetric analysis curve between 300 and 330 and 420 degrees Celsius. Here we can see the temperature and exothermic peak in DTA curves. So this is actually the first step in which is occurred at about 330 degree to 420 degrees Celsius. In this picture we can see this is actually the reaction. 1.8 copper sulfide CuS reacted with 0.8 oxygen and change into Cu1.8 sulfide S and 0.8 SO2, while the same at same temperature range we can also observe the oxidation of CuS and change into Cu2S and sulfur dioxide gas. Between 420 degrees Celsius to onward 475 degrees Celsius, there is a mass gain associated with an exothermic peak due to Cu2S oxidation to Cu2SO4 according to the global reaction. We know that Cu2S is formed in the first reaction, which is carried out at about 330 to 420 degrees Celsius, and Cu2S is formed. So when we move from 420 degrees Celsius to upward at about 475, then we will get like this. The copper sulfide Cu2S is actually reacted with oxygen and change into copper sulfate CuSO4. In the third step, another exothermic peak is actually obtained, and associated mass gain appears in the temperature at about above the 475 to 585 degrees Celsius. So in this step, this event was related to actually a solid reaction between Cu2S, which was obtained in the first step, and copper sulfate to form the Cu2O, which is an exothermic peak, and it's quite obvious in this diagram, and sulfonation of oxide to form to form oxide, which is actually the mass gain. And herein we can say this is actually the reaction of Cu2S with copper sulfate CuSO4 and subsequently change into Cu2O and SO2, while Cu2 oxide, Cu2O and SO2 again reacted with the limited supply of oxygen, or they are using 1.5 mole of oxygen and change into copper sulfate CuSO4. So in the all the presences, also the presence of CuO and CuSO4 and was detected in the melt at about 580 degrees Celsius, probably due to this proposed reaction. So these are the almost proposed reaction. It is believed that this is actually due to the this exothermic peak is actually due to these proposed reaction, in which the copper sulfate is changed into CuO and copper sulfate, sulfur dioxide and 0.0 mole of oxygen, while Cu2O reacted with the copper sulfate and changed into CuSO4 and sulfur dioxide. The formation of CuSO4 continued up to the 653 degrees Celsius. So this is actually the formation of CuSO4. The formation of CuSO4 is continued at about 650, at which an endothermic peak, here we can see, and the mass loss started, at which the endothermic peak and mass loss started. This last stage was related to the actually decomposition of CuSO4 to CuO. This is all about the thermal oxidation of covellite. I do believe that you people get the quite comprehensive details of thermal analysis of inorganic materials. This is all about this lecture. Thank you very much.